Howdy. This is a video on first course in mathematical logic by Patrick Suppes and Shirley Hill. We'll be looking at section 6.4, Truths of Logic, which deals with the so-called rule of logical truth. We'll also be examining some tautologies that happen to be conditionals and proving that they are tautologies. What we will call a truth of logic is true by its form alone. That is, it doesn't depend upon any particular factual premise. For example, if we consider the expression x equals x, or 4 equals 4, or 7 plus 2 equals 7 plus 2, or Thomas Jefferson equals Thomas Jefferson, those are all truths of logic. Generally speaking, any tautology is a truth of logic. For example, P or not P, that's a true statement in any case. Now, the rule of logical truth allows us to introduce into a proof a truth of logic, and we can do that in any line. A truth of logic is a tautology, and because it's a tautology, it's necessarily true, and because it's necessarily true, we can always insert it into any proof. Please take a look at example 1. We want to prove the statement that 2 plus 1 is equal to 1 plus 1 plus 1, but only from a single premise, namely that 2 is equal to 1 plus 1. Can we do it? Previously, we actually didn't have the tools, but with the rule of logical truth, we can complete the proof. Additionally, we need to keep in mind the rule of identity, which was covered in the last section. For line 1, we simply have our given premise, that 2 is equal to 1 plus 1. And that's the only premise we're given. We're not given the premise, for example, that 2 plus 1 is equal to 3. We're not given the premise that 3 plus 2 is equal to 5. We're only given this premise, 2 is equal to 1 plus 1, and that's it. What should we do next? Let's try the rule of logical truth. For line 2, we can just say that 2 plus 1 is equal to 2 plus 1, and that's a logical truth. Something is identical to itself. I'm identical with me. 2 plus 1 is identical to 2 plus 1. And it's a tautology. For line 3, we can now get that conclusion. How? By the rule of identity. After all, line 1 tells us that 2 is equal to 1 plus 1. Or in other words, that 2 is identical with 1 plus 1. So we can take that 1 plus 1 and substitute that in for that 2 that appears on line 2. So for line 3, we can say, therefore, it follows that 2 plus 1 is equal to 1 plus 1 plus 1 by the rule of identity based on lines 1 and 2. Note that for line 2, we use the rule of logical truth. And for line 3, we use the rule of identity. And when thinking of identity, we can also think about substitution. So think substitution. After all, we took this 1 plus 1 and substituted that for that 2. But it's based on that identity that 2 is identical with 1 plus 1. So we got that 1 plus 1 by substitution, and that substitution is based on identity. Let's look at example 2. In example 2, we want to prove Q or R based on two premises: if P, then Q; if not P, then R. The rule of logical truth makes the proof easier here. Otherwise, we would need an indirect proof. So we can do it. We can do a so-called reductio ad absurdum proof. But that will require many, many lines. Here we can only use 4. Much shorter. So this is line 1, is a premise. Here's line 2, a premise. For line 3, think about it. We can use the rule of logical truth, because P or not P is a tautology. So that's a logical truth. You have two options, P or not P. If P is true, that disjunction is true. But even if P is not true, the disjunction remains true. Hence, it's a tautology. If P, then Q. If not P, then R. Hence, for 4, we can say Q or R, because we have a constructive dilemma with lines 1, 2, and 3. I should note that the textbook does not call this a constructive dilemma. Most textbooks do, so I'm just going to stick with standard terminology. But you can see here that the rule of logical truth made this proof, very easy, very straightforward. We will now work on part of exercise 9A from the Suppes Hill textbook. This is on pages 237 to 238, where to derive the conclusion from the given premises. These are actually not too difficult once you get the hang of it, but the feeling of disorientation really is perfectly normal when you first learn something. Once a couple of things click, this will become very easy. Trust me on that. On number 4, we need to derive that 2 times 7 times 15 is equal to 14 times 3 times 5, based on only two premises, that 2 times 7 is 14, and that 3 times 5 is 15. How should we go about this? The first thing is to look at the conclusion. Okay, there's definite overlap between the conclusion and the premises. So we have this 2 times 7, this shows up here in the premises. We have this 15, this shows up here. We have this 14, this shows up here. And we have this 3 times 5, this shows up here. So there's definite overlap. There better be some overlap. And also, we can rewrite that conclusion to help us out. We really have 2 times 7 times 3 times 5 is equal to 2 times 7 times 3 times 5. And that's a good hint in terms of what we should do in terms of using the identity rule and the rule of logical truth. In fact, we really should state this as a logical truth, that 2 times 7 times 3 times 5 is equal to 2 times 7 times 3 times 5. So for line 3, we'll say that 2 times 7 times 3 times 5 is equal to 2 times 7 times 3 times 5. And that's simply a logical truth. However, for this 3 times 5, we want a 15. So let's use some identities here. For line 2, we can say 2 times 7 times 15 is equal to 2 times 7 times 3 times 5. This is an identity with lines 2 and 3. Because in line 2, we're told that 3 times 5 is identical with 15. Now look at line 4. Here we have this 2 times 7. For the conclusion, we want a 14 there. And notice, of course, that line 1 tells us that 2 times 7 is 14. So for line 5, we can say that 2 times 7 times 15 is equal to 14 times 3 times 5. And this is the identity rule with lines 1 and 4. For number 5, we have a lot of premises. We have 5 premises, in fact. So we want to prove that 2 times the quantity 3 plus 4 is equal to the quantity 2 times 3 plus the quantity 2 times 4. If you look at that conclusion we wish to derive, this is actually the distribution rule, okay? Because A times the quantity B plus C is equal to A times B plus A times C. So that's distribution. What should we do first for line 6? How about a logical truth? So for 6, what should we say? Here's an idea. Why don't we state this left-hand side? We have this equation here, right here, and this left-hand side is 2 times the quantity 3 plus 4. So we can say that 2 times the quantity 3 plus 4 is equal to 2 times the quantity 3 plus 4. And that's simply a logical truth. Something is identical with itself. And now we can do the identities. Because notice, what's this 3 plus 4? Well, according to line 1, it's a 7. We can work through all these identities, boom, 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 and we will end up at our desired conclusion. So for line 7, 2 times the quantity 3 plus 4 is equal to 2 times the quantity 7 by the identity, lines 1 and 6. But now notice something. We know that this 2 times 7 is identical to 14. If you just go down the list again, when we do this boom, 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 we will get that good conclusion. So for 8, let's say 2 times the quantity 3 plus 4 is equal to 14. The rule of identity, 2, 7. Line 3 tells us that 6 plus 8 is identical to 14. So for line 9, 2 times the quantity 3 plus 4 is equal to 6 plus 8. The rule of identity, lines 3 and 8. Line 4 tells us that 2 times 3 is identical to 6. So we can get 2 times the quantity 3 plus 4 is equal to 2 times 3, that quantity, plus 8, rule of identity, lines 4 and 9. And look, line 5 tells us that 2 times 4 is identical to 8. So for line 11, we get the desired conclusion. So therefore, it is the case that 2 times the quantity 3 plus 4 is equal to the quantity 2 times 3 plus the quantity 2 times 4 by the rule of identity, 5 and 10. For both number 8 and number 9, we have universal quantifiers. In number 8, premise 1, we have for all x, for all y, x plus y is equal to y plus x. And this is an explicit statement of the commutative property. That x plus y equals y plus x. For example, 4 plus 7 is equal to 7 plus 4. And likewise, for number 9, premise 1, we have for all x, for all y, x times y is equal to y times x. This is also a reference to the commutative property, this time, of course, to multiplication, that x times y is equal to y times x. For example, 4 times 3 is equal to 3 times 4. And then has to be explicitly referenced, explicitly mentioned. And we have it as a premise. For example, let's just say we only have this premise from number 8, premise 3. 3 plus 2 equals 5. Let's say that's the only premise. We could not say from the fact that 3 plus 2 equals 5 that 2 plus 3 equals 5 without the commutative property. So the commutative property has to be explicitly listed as a premise. And we'll see that when we work on these two problems. For number 8, we want to derive that 2 plus a quantity 2 plus 1 is equal to 5. The first thing we'll do is state that 2 plus the quantity 2 plus 1 is equal to 2 plus the quantity 2 plus 1, because that's a logical truth. It's a tautology. So for line 4, we can get 2 plus the quantity 2 plus 1 is equal to 2 plus the quantity 2 plus 1. And that's simply a logical truth. We then have to work on that right-hand side to get the number 5. And I'm sorry, that kind of blotched out that. So, all right. So what should we do next? We can see that 2 plus 1 shows up in premise 2, 2 plus 1, and that's identical to 3. So that we can use the identity rule right away. So for 5, we can get 2 plus the quantity 2 plus 1 is equal to 2 plus 3 by the rule of identity with lines 2 and 4. We have this 2 plus 3. That's not written the same way as 3 plus 2. So we cannot use the rule of identity yet. We're going to have to use the commutative property, which is stated in premise 1. For line 6, we'll instantiate. We'll say for all y, x will be 2, so we'll say 2 plus y is equal to y plus 2, and that's just the universal instantiation of line 1. For line 7, we'll instantiate the y, so we'll say 2 plus 3 is equal to 3 plus 2 by the universal instantiation line 6. So let me just write note we need commutative property. Okay, that's the only way we could have got line 7. So now note we have this 3 plus 2, and according to line 3, that's equivalent to 5. So for 8, we can say 2 plus 3 is equal to 5 by the identity rule with lines 3 and 7. Moreover, this 2 plus 3 appears in line 5, and we know that 2 plus 3 is identical to 5. So for 9, it does in fact follow that 2 plus the quantity 2 plus 1 is equal to 5 by the identity rule with lines 5 and 8. For number 9, we want to derive 2 times the quantity 5 times 7 is equal to 70. So once again, we'll start out using the logical truth rule. We'll say that 2 times the quantity 5 times 7 is equal to 2 times the quantity 5 times 7. It's a logical truth. According to premise 2, 5 times 7 is identical to 35. So for line 5, we can get 2 times the quantity 5 times 7 is equal to 2 times 35 by the rule of identity with lines 2 and 4. Once again, note we need the commutative rule or the commutative property. Because we have this 2 times 35, but here we have 35 times 2. We have to make use of the first premise, which is a commutative property, so we will instantiate. For line 6, we'll say for all y, we'll say 2 times y is equal to y times 2, universal instantiation of line 1. For 7, we'll instantiate that y, so we'll say 2 times 35 is equal to 35 times 2 by the universal instantiation of line 6. Now we have that this and this are identical. For 8, we could then say that 2 times 35 is equal to 70 because of premise 3. And then for 9, we can say therefore 2 times the quantity 5 times 7 is equal to 70 by the identity property. I'm sorry, I should have put identity here too. That's identity. For line 8, it's the identity with lines 3, 7. For 9, we have the identity between lines 5 and 8. This will be the last problem in this video. It comes from exercise 9b on page 239. We're to give derivations of the following tautologies. A derivation, not a truth table. We could do a truth table, but here we want a step-by-step proof. For number 2, we have overall conditional, and we'll do a conditional proof. However, in this derivation, and others like it, in our proofs we must make assumptions within assumptions, and there's no problem there. We can do that. So overall, we'll do a conditional proof. We'll assume the antecedent to try to derive the consequent. But with that conditional proof, however, we will do an indirect proof. We will assume the contradictory of this consequent. And insofar as we can show a contradiction based on the secondary assumption, the apparent consequent must follow, and based on the conditional proof, it must really be a consequent based on the assumption of the antecedent. So for line 1, we're going to assume that antecedent, we'll say P and parentheses Q or R, close parentheses, and this is just an assumption. And because it's an assumption, we'll place it under quarantine, so to speak. And then within that assumption, we'll make a new assumption. So the first assumption here is based on doing a conditional proof. Our second assumption is an indirect proof. We'll assume not brackets, parentheses, P and Q, close parentheses, or parentheses P and R, close parentheses, close brackets. And this is our assumption 2. And this assumption, again, is our indirect proof. Let's do De Morgan. So we'll say not, parentheses, P and Q, or, we have to change that to a conjunction, and not P and R. So De Morgan on 2. For 4, let's simplify. We can get not P and Q. So that's a simplification of 3. And likewise, we can get not P and R and not P and Q by the commutative rule with line 3. And then we can simplify to get not P and R by the simplification of 5. We can apply De Morgan's rule on line 4. So for 7, we can get not P or not Q, De Morgan 4. Likewise, we can do De Morgan on 6, so we can get not P or not R, De Morgan 6. For 9, we can get P by the simplification of line 1. For 10, let's double negate, not P, double negation 9. And from that, we can get this not Q by disjunctive syllogism. So for 11, we'll get not Q, disjunctive syllogism, 7, 10. And likewise, we can get this not R from 8. So for 12, we can get not R, disjunctive syllogism, 8, 10. For 13, we'll do the commutative rule on line 1, so we can get Q or R and P, commutative rule line 1. For 14, we can simplify to get Q or R, simplification 13. We have this not Q from line 11, so we can get this R from 14. So for 15, we can get R by our disjunctive syllogism, 11, 14. We have a not R here and an R here. So for 16, we can get not R and R by the conjunction of 12, 15. But this is a contradiction. So for 17, we can then say it is not the case that brackets, parentheses, P and Q, close parentheses, or parentheses, P and R, close parentheses, close bracket, by our indirect proof with lines 2 through 16. So for 18, we can then just get P and Q or P and R by double negation of 17. And this is identical to this consequent. So for 19, outside of quarantine, it therefore follows that P and Q or R, arrow P and Q, or P and R by our conditional proof with lines 1 to 18. Up next is section 7.1, commutative axiom. It's part of a new chapter which we will build a simple mathematical system, so that'll be pretty neat. And the remainder of these videos, we will finish up the Suppes Hill textbook. There are 4 sections for chapter 7, and there are 2 sections for chapter 8, and we will conclude after that.